All right, in the last lesson, we looked at just how to write ratios and not so much how to solve them, just making sure we're getting the order right, looking for wording in those kind of scenarios. In this lesson, we're going to look at solving direct proportions. So we're going to take those ratios and we're going to put them to use in order to calculate something. Now we're going to look at some more of this in your next semester. In the next semester, we'll spend a little bit of time looking at how ratio affects slope and those kinds of things. But we're going to kind of get an introduction to some of it here. And we're going to look at a few application questions. There's a million kinds of questions that we could use. So you'll have to bear with me because I can't go through every example that's possible, but we'll try get a number of examples in for you here. So by the end of this lesson, you should be able to solve what's called a direct proportion. Now, proportion is just a way of saying that two ratios are equivalent. So on a scale, we'll say a 1/4 inch equals a foot. That means if I measure 1 inch on my plan, if I was to reduce the ratio of the actual measurement to the plan measurement, it should reduce to a 1/4 inch equals 1 foot. Now, there are some scenarios in carpentry, this is one, where we will leave a 1/4 inch equals a foot and we'll just leave it as a fraction. We won't get rid of the fraction. So as much as oftentimes we'll say, okay, let's get rid of the fraction in order to find our ratio, there's times in a trade where you won't necessarily do that, and scale is one of those examples. Now, here's just an example. We have a scale marked on this plan here. I'm just waiting for my tablet to wake up here. So we have a scale marked on the plan here where 1/4 inch equals a foot. So on this plan, you know that this measurement is 14 feet. So we could calculate, if we were going to sketch this out on paper, something you would have done in your blueprints course perhaps, is what would that actual measurement be? So we have an example where we'll look at that towards the end of the lesson. I think it's the last example that I have. This will take a scale and we'll take a scale and we'll convert it to what's an actual measurement. Again, we're going to have some more examples of that come up next term when we kind of look at some applied examples. Unfortunately, our course has been split into two components. So our first semester is kind of a quick overview, and then second semester is, okay, well, let's put this in some project-based examples. If it was up to me, perhaps I would structure your course a little differently, but the curriculum advisors and the college board of directors, they adjust sometimes the way that our courses are delivered, so it changes maybe what would be ideal for you as learners. So we can continue to have that fight later. So the biggest thing at this point, proportions, we're solving proportions, and these are two equal ratios. So proportion algebra, you need to know a little bit of algebra. So this is going to be your start to algebra. And then by the end of next week, you'll be into a little bit more algebra. We're going to get into a little complicated stuff after this, but this is easy algebra for us. So this should take you back to equal fractions. So you've seen algebra that's similar to this. We need to identify what would x be in order to make 7 over something equal to 8 over 15. Now to do this, we know that these two ratios have to be equal. If they're equal, we're going to solve it the same way we would do for equal fractions. We know that if we multiply these two together, so I'm going to write that as 8x, and we multiply these two together, 7 times 15, they have to be equal. So 8x is equal to 7 times 15. We call that cross multiplication, because we multiply across, okay? We multiply on the diagonal and it makes an x. Sketching the x in often helps people when they're solving it to make sure you're multiplying the correct things together. We don't need to worry about common denominators or anything like that. So we're going to take 7 times 15 equals 8 times x, or x times 8, same thing. So let's solve that. So we have 8x. And that just means 8 times x, when we put a letter and a number next to each other, equals 7 times 15, which is 105. Now we need to get x alone. We don't want to solve for 8x. We want to know what 1x is, because 1x is what's on the bottom. So we have to undo the math. And to undo the math, the opposite of multiply is to divide. So we're going to divide both sides by 8. You'll notice this 8 over 8 here gives us a fraction that's equal to 1. We often say we cancel them out. It's not that they go to 0, but they create a 1 for us. So now on this side, we're left with x equals 105 divided by 8. We can put that in our calculator, and you will get 13.125. And I didn't tell you where to round to. So we're going to round to the nearest 10 because the next slide will tell you to go to the nearest 10, which is going to give us 13.1. So pretty easy algebra. Simple thing to solve, cross multiply and divide. So I'm going to do 4 more examples with you just to make sure you know how to do it. Cross multiplication is one of the more important pieces of algebra to do. So, and you have to have it for all of the ratio stuff. All right. So we're going to solve this one. So we have 16 over 36 equals n over 72. We could reduce this further, but we don't need to because we just want to find out what n is. So we're just going to use some algebra. Yes, it means our numbers are going to be larger, but you have a calculator, so that's not a big deal. So 36 times n gives us 36n. That needs to be equal to 16 times 72. Now that we have that, 36n equals 16 times 72 gives us 1,152. 36n, we need to divide both sides by 36. 36 is canceled, leaving us with 1n is equal to 32. All right. So pretty straightforward. I find sketching in the X often helps. Let's jump over to the next one. 24 over 42 equals 64 over X. Well, 42 times 64 equals, I'm going to do 24 times X. 42 times 64 leaves us with 2,688. Just put it in your calculator. Is equal to 24x. Divide both sides by 24. X equals 112. And it doesn't really matter which side you can write x equals 112 or 112 equals x. Either way, it's going to work fine for us. All right, let's look at the next one. So we're going to multiply across. 51.2 times b leaves us with 51.2b is equal to 25 times 12.2, 2.5 times 12.4. Putting that in your calculator, 51.2b is equal to 31. Now we divide both sides by 51.2. 51.2 cancels on both sides, leaving us with b is equal to 0.6. Now here's a way to check your work and see does it make sense. Small number on top, much larger number on the bottom. That should be true on this side as well. So if the small number is on the top and b is on the top, your answer should be smaller than the denominator. So it's just kind of one of those little fact checks. If it's not smaller, it means maybe you flipped your order around. Usually a really simple fix. Let's jump over to the next one. 1 times z gives us just z or z, whichever way you want to say it, equals 0.25 times 7.5. Z is equal to 1.9. So pretty straightforward, cross multiplication. These ones are always the easiest when you have a 1 involved opposite the z because it's a little less rearranging for us. So you've got a number of those for practice questions in your book. I recommend go through as many as it takes in order to kind of memorize that process. because knowing how to cross multiply and divide is something that's really important. And it's one of those things you just kind of have to practice it and see if you're getting it right. All right. So there's going to be a couple of those in your quiz on SAM you'll be looking for. Now what we're going to do is we're going to put them into word problems. I'm going to just adjust up here. So we're going to put things into word problems. And now we have to actually write the two equal ratios. So for this example, and I like this one because it's just, we can see it, it's visual, and I know it's not trade related, but it works for us to kind of understand some of the more complex problems. If a fruit bowl is filled using the same ratio of oranges and apples, how many oranges will there be in a bowl with 50 pieces of fruit? So the first thing to look at is think, what are we looking for? So we're looking for oranges, and we're comparing that to total fruit. That means we need to make a ratio that uses what we know and compares oranges to total fruit. So, well, we know there's 4 oranges to 5 total. Okay, we know there's 4 oranges to 5 total fruits because we can just take that from our picture. There's 4 oranges here. We have 1 apple. There's 5 pieces of fruit total. Well, if I have a bowl full of 50 pieces, I have 50 total. You'll notice I'm matching up the units, total on the bottom, total on the bottom. I'm matching the units. Matching your units is going to make a difference. And then I want X oranges on the top. These two ratios should be equal to each other. 5 times X equals 5X. 4 times 50 leaves me with 200, and then divide both sides by 5. 5's cancel, and X is equal to 40 oranges. Now, I like to use words to put them in my equation. It helps me line things up, but not only that, it helps me remember what the number that I'm getting at the end happens to relate to, because you're always going to have two quantities here. And I need to know, is that 40 the number of oranges, or is it the amount of fruit in the bowl? All right, example 2. Now this question that maybe doesn't look like a trade question to you, but it's actually a really good question for people working in trades, because oftentimes you'll end up working with dilutions. So you may have to, okay, for example, diluting a chemical spray, or maybe fertilizer is one that I can think of. I'm thinking of examples that I see in my work, in just things that I use at home. So diluting fertilizer is something that you often have to do. Sometimes you get a concentrate and you have to figure, okay, so if I want to dilute it and get it the right ratio, how do I do that? This year we were putting a weed killer on our yard. So we have a large cement patio, and we needed to get rid of the weeds that were in between. There's a few things you can use to do that, but one of the products we were using, we were talking to them at the nursery, we had really good luck with it, but they were saying that other people weren't. And I think one of the biggest factors is if you don't know how to mix it properly when you buy the concentrated version, if it's not strong enough, then you don't get the desired effect. So that's just an example. Concrete. Mixing concrete would be a really good example of this. So it'll tell you how many grams or how many parts of cement you need to water, or how many parts of cement you need to gravel. So it's the same kind of question as you have with this one. This one just happens to have a really good visual for us. So in this question, we're mixing water and soap. It could be any kind of thing you happen to be mixing. One that my husband does, he often has to mix gas for his chainsaw, and it's a 50-to-1 ratio. So he needs to know how much fuel to buy, to put how much oil in to get the mix right, or else the chainsaw's not going to run correctly. So there's lots of little examples where you can see that kind of thing show up. So you might think this one doesn't relate to you, but you never know where you could see it later, and you might even just see it in normal household stuff, even if it's not something you're using in your work. All right. So for this one, we want to find how many milliliters of soap we need to make 5 liters of soap solution. So I want to know how many mils do I need to have in order to make a total of, whoops, I wrote 6 here. I didn't need to write 6. I want to know how many mils in order to make a total of 500 or 5,000 milliliters or 5 liters. I've done that. I've switched to milliliters. The reason I switched to milliliters is I want to know milliliters at the end. So we'll take our liters. 5 liters equals 5,000 mils. Okay. So this is a question that works quite nicely for us. There's a question in the SAM quiz that talks about parts of a board, and the parts of a board question works exactly the same as this soap question. So keep that in mind if you get stuck. So we want to make a total of 500 mils, and I want to know how much soap. So I'm comparing soap, concentrate, to total. Well, what is that ratio? If I look over here, I have 1 part of soap to how many parts altogether? Well, there's 6 parts altogether. So there's 1 part soap to 6 parts. I'm just abbreviating so I have enough space to write it. Total. All right, now we can plug in our information. So I know the ratio has to be a 1 to 6. Well, how many mils of soap have to be put in order to make 5,000 mils? Now, if it's 1 part to 6 parts, we're going to be comparing mils to mils. So if you put liters in the bottom here, you would get liters of soap out. When it's parts and parts, same unit on the top, same unit on the bottom, that means on the other side, we have to use same unit on the top, same unit on the bottom. So I'm comparing the quantities. So in order to solve this, I'm going to put an X where my question mark is. 1 times 5,000, leaves me with 5,000 equals 6 times X. Divide both sides by 6. And X is equal to 5,000 divided by 6, leaves us with 833 mils of soap. So I would have to take 833 mils and add that in order to make a 5-liter solution. This is something that with needing to do proper disinfection of things, this is something that actually comes up quite often. And I know I never measure when I'm at home how many mils of Lysol or whatever it is you have to put into your solution for mopping floors or whatever to be properly disinfected. But I know if I have a client coming in to do alterations, if I'm wiping doorknobs, I do watch the ratio to make sure that I'm mixing it to the right ratio to properly disinfect so that I'm covered, so that I've been safe for any clients that are coming for alterations or anything like that. Thankfully, this time of year with school in, I don't have to worry about that too much. That's just a summer thing, and I'm hoping by next summer we'll be through the COVID crisis. All right, for our next example, we're looking at shapes. So in this question, 2 shapes are similar if their angles are the same. So if 2 shapes are similar, so these 2 triangles are similar, so this one has a right angle here, this one's not drawn in, there should be a right angle there. So these 2 shapes are similar. If they're similar, then their sides will form equal ratios. Okay, so the ratio of side AB to side BC should equal the ratio of side DE to side EF. So these ratios should match. So just because these 2 sides are connected, they're the right sides of the angle, and these 2 sides match. I'm going to call that side X. All right. So since the triangles below are similar, what's the length of missing side EF? Or we'll call this side X, just because it's easier if we only have one variable. Now, this is the whole principle behind why we can use a pitch ratio for a roof. So you'll often see a 512 pitch, and then you have to figure out, so you know if you have a 512 pitch and you have a little triangle, I always have to think rise over run. So it's a 512 would be your little triangle. Now, if we have a big roof and you know that half the width of the building is maybe 12 feet, what would the height be? And we can solve that because of these similar triangles. So if we can solve a similar triangle, you'll be able to solve a roof pitch question. You just have to remember that whenever we do a roof pitch question, we only deal with half a triangle. So I'll try to give you an example of that. I don't think I'll put one in the slide, but we'll add one in at the end if you happen to get stuck with it. So let's first set up our ratio. So we know that 8 to 24, so this side, these two sides should form the same ratio as these two sides, or 8 and 24 should have the same ratio as 6 and whatever X is. It doesn't matter which way you think about it. What I'm going to do is I'm going to say big triangle and small triangle. Okay, those are the ratios I'm going to compare. Equals, and we have two ratios. So now we need to look at the sides that match. So the big triangle, I have side that's 24 long, and on the little triangle, that side is 8 long. So I'm matching up similar sides. On the other side, on the little triangle, we have a 6, and on the big triangle, we have an X. So that's what we're going to put here, and we're going to keep the orders matching. If we put the big triangle on the top and a small triangle on the bottom. I'm going to show you another way you can write it, because you could write it another way. 24 times 6 is going to be equal to 8x. 24 times 6 leaves us with 144 equals 8x. Divide both by 8, and x equals 18. All right. You could, I'll put it up here just because there's space. You could also say, if you wanted, that you could say small triangle this way equals large triangle. And you could compare the two sides that way. You could say 8 over 6 equals 24 over x. 8 times x, you're still going to get the same thing. 6 times 24, you're going to get 144. So that's another way you could write it. Both of those are equally correct. If that's confusing, please reach out to me. I'm happy to go through it with you. Because there's more than one way to write a ratio, sometimes it's hard to give a one option only example. All right, this is a great question, really good question. So this actually, I checked the code book for codes on this. So unless it's changed recently, this should be what you would find in your code book. A standard wheelchair ramp should have a grade no steeper than 1 to 12. So that means for every inch of rise, so change in height, we should have a 12-inch run. So whenever they give a grade or a slope, it's always rise and run. Same thing for a roof. It's always going to be rise first. You rise before you walk is the way I was told to think of it. So it's always rise first and then run. So here it says, if a door is 2 feet 6 inches above the ground, how long would a wheelchair ramp need to be in feet and inches? And it recommends sketching a diagram, which is a good tool. So we're going to do a quick sketch. So we know we need to build a ramp. And we know that this is 2 feet 6 inches. And we want to know, well, how long or how far out does this need to be? Now, our specs say, if we look here, that we have to have a 1 to 12 ratio. So that means 12 inches this way, 1 inch that way. Or it could be 12 feet out this way and 1 foot rise. So if you want to think of it as a little triangle and a big triangle, think of this as our little triangle. It has a 12 to 1. And then this whole side happens to be X. All right. So I'm thinking of it kind of like two triangles again. Now, You know you can't multiply when you have mixed units, so let's switch this all into one unit. So we can say this is 2.5 feet. It'll make us give us easy calculations. You could have switched it all into inches if you want. It's all the same difference. So you know you need a rise, run. Rise and run is going to give us 1 over 12 is equal to, well, the door has up 2.5 feet, so we're going to put 2.5. And that means we have a run of x. We know how far out is the ramp going to end up being. So 1 times x is just x. 2.5 times 12 happens to give us 30. So x gives us 30. And if I'm a good person, good mathematician, I would say we have 30 foot or 30 feet of run. So pretty easy calculation, not too bad. Hopefully I haven't confused anybody yet. The next question is a nice, easy one. I find sometimes the rise run ones are a little bit tricky and it's just more wording. This one is usually pretty straightforward. Maintenance on 7 trucks for a year costs $870. What's it going to cost to maintain 9 trucks? Well, 7 trucks cost us $870. Add more trucks should go up. So this is why we call it a direct relationship. One quantity increases, the other increases. We'll look at the opposite example of that later. So let's set up a ratio. Well, we know 7 trucks matches up with $870. Okay. Well, that should be equal to 9 trucks at X dollars. So we have a really simple ratio. 7 times X is equal to 870 times 9. I've left my units out when I'm writing here just because sometimes it makes it a little easier to see. So 7x is equal to 7,830 divided by 7. X is equal to $1,119 because we had to round up to the nearest dollar. So watch your rounding and we'll put our dollar sign in. You'll notice I put dollar signs by my X to remind me that this was in dollars and this should also be in dollars. You could have also found out what was the cost for 1 truck and then multiply that by 9. That works as well. So there's a couple ways to solve this particular question. I've got 2 questions left in the month. A blueprint is drawn with a scale of 1 foot equals 1/4 inch. So this kind of takes us back to the beginning diagram that you had, and I think you've probably done this in blueprints before. If a 6 foot by 20 foot garage is drawn, how many inches is it going to measure on a plan? So we just need to solve 2 simple ratios. So I will typically switch these to decimals first. So 1 foot equals 0.25 inches. I find it easier to work with decimals in your calculator. I know we did all that fraction stuff. The fraction stuff appeases everybody else. We do need to know how to use fractions. But there are times when it's easier to go to the decimal and then switch back. And this is one of those times. So 1 foot is 0.25 inches on our plan. If we have 16 feet on the plan, how many inches will that be? So it's a pretty simple calculation. 1 times x gives us x. 0.25 times 16 leaves us with x is equal to 4. And you'll notice there's inches on the bottom here, so it's going to be inches there. So that garage, the 16-foot wall, is going to be drawn at 4 inches long. Same thing for the 21. 1 over 0.25 is equal to 20 over x. So x equals 0.25 times 20. X is equal to 0.25 times 20 gives us 5 inches. So those were our 2 measurements, length and width. So if we're going to draw it, we're going to have 4 inches by 5 inches on the plan. Not too bad. Okay, So now we have another plan and we have a rule on it, and they didn't mark it with feet and inches. I know oftentimes things are marked with feet and inches, but in this case, we're saying they didn't mark with feet and inches, and you've just measured it out. And you've measured that it's measuring 3 1/16 by 4 3/16. How big is it actually? Well, let's solve it. So the first thing I'm going to do, let's switch to decimals because it's going to be easier for us to measure. So 1/16 is 0.0625, so 3.0625 inches. And this one is going to be 4.1875 inches. And we want to answer for our plan in feet and inches, so we'll see what we can solve for that. So these are our blueprint plan. So we're using the same scale. So we have 1 foot equals 0.25 inches. That should be equal to x feet over 3.0625. Solving this, 0.25x equals 3.0625. Divide both sides by 0.25. And x is equal to 12.25 feet. You'll notice feet on the top here, feet on the top there, inches on the bottom, inches on the bottom. So our answer is in feet. 0.25 feet is how many inches? 0.25 feet times 12 gives me 3. So that's equal to 12 feet and 3 inches. Whenever I think of blueprint measurements, I always think of my dad. I would have been pretty little. I would have only been about 5 when my father designed our house. He's not an architect, he's not a carpenter, but he really likes drawing and plans and that kind of thing. And he was teased for years about his paper house because he took our entire house, drew it to scale. But not only did he draw the house to scale, he also drew the furniture to scale to make sure that bedrooms would fit exactly what he wanted, and the space was optimized. I would argue it probably made our bathrooms too small, but we all had generous sized bedrooms. But it was several years in planning this house and just rearranging paper furniture in the rooms to see what would work. So it can actually be a really practical skill if you're trying to come up with plans. I'm in the process of trying to design a renovation for our basement. And at this point, it's time to start doing to scale sketches on paper. So maybe next semester, we'll be able to actually look at some real numbers and we can do some comparisons with, well, what would you do if? Sometimes it's nice to work with a real project. And I always like it when I have something that reminds me of what you would actually have to calculate and how you might have to communicate it to somebody working in the trade, because it's one of those jobs. Putting up walls downstairs will probably involve me hiring a carpenter rather than trying to play carpenter. It's probably better for me and my spouse if we hire somebody instead of, well, let's just say arguing through it ourselves. Many of you in relationships, you probably have experienced that on occasion. All right, so let's figure out the other dimension for this room. So we did the 3 1/16 inches. Now we're going to do the 4 3/16 inches. So we still have 1 foot is 0.25 inches is equal to x feet over 4.1875. And if you solve this one, I'm going to just leave the algebra to you and I'm going to give you the answer. For x, we're going to find x is equal to 16.75 feet, or x is equal to 16 feet and 9 inches. So I'm going to let you solve that one because I'm probably starting to bore you at this point in the lesson. I don't like to keep a lesson any more than 20 to 30 minutes, and I think I'm probably at the limit of that right now. Our last example we'll do is we're going to do an example where we want to level something. So we want to figure out how much should we raise one end. So this could easily be a scenario where you're trying to maybe level a level a shed or something like that, and you're trying to put slopers underneath. I want to say slopers, sleepers underneath. Get the right word. That you can set it on. So you want to make sure everything's level before you drop the shed on. We've done this one before at our place, so it's kind of familiar to me. So in this case, we've got a 10-foot distance. Now this is obviously not drawn to scale, but we have a 10-foot distance and here, and I've got a 4-foot level. So maybe I should read the question first to tell you where those numbers are coming from. So it says a 4-foot level is used to level a 10-foot piece of lumber. When the level is level, sounds like a tongue twister, there's a gap. So when this level is showing bubble in the middle, between the end of the level and the piece of lumber, there's a gap of 7/16 of an inch between the end of the level board. Sometimes it's a hard question to word, that's why I put pictures in with it. How much must point B be raised? So I want to know, well, how much would I? Let me just go back here. Not sure what happened there. So we want to figure out how much would that particular height be. So pretty easy for us to do. So we know that if we go out 4 feet, we drop 7/16 of an inch. So that's one of the ratios we have. So 4 feet drops 7/16. All right, so if I go out 10 feet, how much should the drop be? That's telling me how much I have to raise the end. And that's going to give me inches because I put 7/16 in inches over here. So in order to solve that, let's turn everything into decimals. 4 feet and 7/16 is 0.4375 inches is equal to 10 feet over x. 4 times x is equal to 10 feet times 0.4375 is going to give us 4.375 and divide both sides by 4. 4's cancel here. X equals 4.375 divided by 4. X is equal to 1.09375 inches. Now, if you go back here, it says answer to the nearest 16th. Well, to get to the nearest 16th, 0.9375, there's another 0 in there, times 16 equals 1.5, which is rounds up to 2. So we'll have 1 and 2/16, or 1 1/8 inches that I need to raise this end. So this is equal to 1 1/8, or 1 1/16. So this is one of those questions where now Sam isn't going to get you to go to 16ths. I put that in there to kind of get you going back to those. Eventually you'll get a paper assignment that you'll hand in and you'll be able to solve a few of those pieces for it, but don't lose how to go to 16ths. And hopefully that gives you what you need to know. I am going to just pop in really quickly. I'm going to throw in a blank slide just to give you a little tip. So let me see here. I'm going to find where. I should be able to give us a blank slide. Well, I can't see where to give us a blank slide. So let me just insert a slide and we'll just quickly give you a sketch. So one question that you could see is a roof has a 5/12 pitch. So that's going to be always rise and run. Okay, so roof has a 5/12 pitch. If the building is, let's say 20 feet wide. What is the height to the peak? Okay, so in order to solve that question, think about your building. Now we have to be a little bit careful when we do these ones. So we have 20 feet across the bottom, but whenever you do pitch, pitch is always, the run is only half. It goes to the highest point. So when we do pitch, we're looking at a small triangle like this one, where we have a 5 rise and a run of 12. Okay, so when you're solving this and I'm looking for height, I need, so if 20 is the total distance, I need to make sure I just use 10. Okay, so this 5 and 12 only uses a small triangle. And since I'm only using a small triangle, so since this uses a small triangle, I need to use the part of the roof that's just a small triangle. So that means I'm going to use 10 instead of 20. So just one of those little tips as you're going, if you happen to get stuck and you're going through the questions, you're going, oh, how in the world do I do that one? Because she didn't give it to us exactly. There's how you do it. I'm not going to solve it for you. I want you to think about it. So it's not too complicated. I think you should be fine with it. And let me know if you have any trouble.